In this tutorial, we will be discussing the discovery of the nuclear atom. Atoms compose matter. Their properties determine the matter's properties. An atom is the smallest identifiable unit of an element, and an element is a substance that cannot be broken down into simpler substances. So let's refresh. Atom makes up the elements. There are about 91 different elements in nature, and consequently about 91 different kinds of atoms. Scientists have succeeded in making about 20 synthetic elements that are not found in nature. The exact number of naturally occurring elements is controversial because some elements previously considered only synthetic may actually occur in nature in very small quantities. Leucippus and Democritus noticed the years 5th century BC and 460 to 370 BC were the first recorded ideas of atoms. Democritus suggested that if you divide matter into smaller and smaller pieces, you may end up with tiny indestructible particles. So if you take let's say a piece of paper and you cut it in half and cut it in half again and again and again and again and make it smaller and smaller and smaller, eventually you're going to get to a point where you can't cut it in half anymore. Democritus called this atomos, or atoms. That's where we get that word from, atom, meaning indivisible. You cannot divide it. Democritus is the first person on record to have postulated that matter was composed of atoms. Over 2,000 years later, in 1808, John Dalton, a professor from England, formalized a theory of atoms that gained broad acceptance. His atomic theory had 3 parts, and you'll notice that it's not actually 100% accurate, but it did give us a starting point since we had to wait 2,000 years to get to this point. Each element is composed of tiny indestructible particles called atoms, just like what Democritus had said. We know now that we can actually destroy an atom such as the atomic bomb by breaking apart the nucleus, or just the fact that it has different parts in it, such as protons, neutrons, and electrons. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. The same mass part is also incorrect because now we know we have isotopes, which will once again be discussed in a future tutorial. Atoms combine in simple, whole number ratios to form compounds, and that part is true. An English physicist named J.J. Thomson, 1856 to 1940, so not far after John Dalton, discovered the smaller and more fundamental particle called the electron. He stated that electrons are negatively charged and are much smaller and lighter than atoms. Electrons are uniformly present in many different kinds of substances. He proposed that atoms must contain positive charge that balance the negative charge of the electrons. So this is what his model showed. They call it a plum pudding model. And this is actually representative of an English dessert. Remember, Thomson was from England. So he said that in this purple sphere, there was a positively charged purple area. And these yellow dots here are the negatively charged electrons. From there, in 1909, Rutherford tried to experiment with this further. He thought that if he took all the electrons out of an atom and he shot it to through a piece of gold foil, kind of like an aluminum foil but made out of gold, really thin piece of gold, they would shoot right through because there would be nothing left once you took away the electrons. But that's not what happened, and this later became what was known as the gold foil experiment. Notice this ring around it. There are alpha particles in here, which alpha particles are a helium atom with no electrons. So you have 2 protons, 2 neutrons, and nothing else. There's no electrons in those. And he thought by removing those electrons and shooting it through this gold foil, it's going to pass right through. This piece of here is a detector. Sorry, this is a detector to determine where those alpha particles hit. And he thought they would all be concentrated at the very, very end. But what ended up happening is that the nucleus of the helium atom and the nucleus of the gold foil atoms ended up bouncing off of each other, and they ended up scattering about. And the fact that they're scattering about told Rutherford that there must be something else going on here and not just the electrons. So most of the particles passed directly through the foil. A few, however, were deflected, some of them at very sharp angles, so almost right back at the machine. So if the plum pudding model was correct, the alpha particles would pass right through the gold foil with minimum deflection. That was his hypothesis. But what actually happened is when the alpha particles hit the nucleus of the gold foil, it ended up ricocheting off. And that helped Rutherford develop the nuclear theory of the atom. Most of the atom's mass and all of the positive charge are contained in a small core called the nucleus. Most of the volume of the atom is empty space through which a tiny negatively charged electrons are dispersed. The number of negatively charged electrons outside the nucleus is equal to the number of positively charged particles, called the protons, inside the nucleus, so that the atom is electrically neutral, because the positives of the protons and the negatives of the electrons cancel each other out. And so this is how we get our image now. The nucleus is in the center with the protons and the neutrons, and the electrons are drifting around it. Now, this has been developed even further and to be more specific, and they've discovered more particles. However, for now, this is where we're staying. So let's take a look at this. The protons and the neutrons ended up having very, very similar mass. If you look at here, notice that they're all to the negative 27. So that way we're comparing apples to apples. But notice that the electron is smaller. The decimal place, the number in front of the times 10 to the negative 27 is much smaller. But the protons and neutrons are fairly similar out to the thousandths place. Also, let's look at the charges. Protons are a positive 1, electrons are a negative 1, and neutrons are a 0. So when we start calculating the masses, we're looking at the protons and the neutrons. When we start looking at charges, we're looking at the protons and electrons. The electrical charge is the fundamental property of the protons and electrons. The positive and negative electrical charges attract each other, while the positive and the negative repel each other. Opposites attract. Same charges repel. Positive and negative charges cancel each other out so that the proton and an electron, when paired, are charge neutral. They have no overall charge. So let's do one small practice problem. An atom composed of which of these particles would have the mass of approximately 12 AMU? Let's go through these. So A, 6 protons. That'd be 6 times 1 and 6 electrons. So this would then equal 6 AMUs approximately, and this would be nowhere near equivalent. This would equal to 6 AMU, which that would not work. 3 protons and 3 neutrons, so that'd be 3 times 1 and 3 times 1, with a total of 6 AMU. The AMUs, the mass coming from the electrons, are so small is insignificant. 6 protons and 6 neutrons. So 6 times 1 is 6. 6 times 1 is 6. So 6 plus 6 would equal 12. That would work. And then 6 electrons then wouldn't matter. And then finally 12 neutrons. 12 times 1 would equal 12. However, in order to have an atom, you absolutely have to have protons in there. Otherwise, it's not considered an atom. It's nothing. This would not even exist. So it'd be C, 6 and 6. And that is the discovery of the nuclear atom.